Okay, should we start?
Yes, please.
Okay, good. So now I've just explained to you about what is SEM. We want to create a model and then use the software to give us all the estimates such that we can find a fitted covariance matrix which is as close as possible to our sample covariance matrix. If they are very close, then we will say that, hey, we should have identified the relationship among all those indicators in, in our sample or population. So again, this is the equation to show to find out the covariance matrix in fitted covariance matrix. Now, SEM, there are 6 steps. It is modified from here to now. Okay, I didn't follow their 6 steps, but these are modified. You can see that the 6 steps are actually divided into 2 parts. The first part is a measurement model, and the second part is a structural model. So step one is to define the individual constructs. That means what items are used to measure which construct and the level of measurement. Are you talking about a multi-level model? Is it um, within or between model? Okay. Then you develop and specify the measurement model. You draw the diagram. I always ask people to draw the diagram on the paper. Whatever you can draw on the paper, you can write out the SEM syntax, no matter whether it is level 1 or M plus. So draw the diagram. Then you need to decide something about the covariance versus correlation. Typically, we should allow the estimation based on covariance matrix to not run correlation matrix because correlation matrix have fewer information and it will provide biased estimates of the standard errors. The identification decision, okay, whether how you want to identify your model. We'll talk about this very soon. Whether you want to fix the first item of the factor loading of the first item to 1 or standardize your latent error. Estimation technique, whether you want to use maximum likelihood or MLR, maximum likelihood of robust standard errors, etc. How you are going to handle the missing data and whether your data are listed or not. Okay, so we need to make a few decisions. We will go over this one by one in the next 3 days. And then we need to assess the quality of the measurement model. We need to look at the overall model fit. We need to look at the construct reliability, convergence, and discriminant validity. That is what we are going to do tomorrow. Assess the quality of your measurement model. A lot of times, many times, I noticed that management researchers are not paying enough attention to the quality of the measurement model. I read, I rerun a lot of published articles and noticed that their convergence validity, particularly convergence validity, are sloppy. Okay, they didn't get a good measurement model. If you are not measuring what you want to measure, then you should not test your hypothesis. You must demonstrate that you are measuring what you want to measure. After you have demonstrating you have a good measurement model, then you can specify your structural model and then test your structural model. The model fits, direction, and the size. So step 1 to step 4 are based on the measurement model, and we want to test whether whether you are measuring what you want to measure well. And then after we have established that, we test the structural model. And you will notice that all studies at the very beginning of the analysis, they will talk about the measurement model, whether they are measuring their variables well. But management studies are not doing a good job. Okay, so we will talk more about this tomorrow. So what are some basic SEM models? We'll go through these basic SEM models in these 3 days. And then when I come in person, I hope the typhoon is not coming with me. Yeah, I read the news that there's a typhoon. There may be a typhoon in Taiwan. So the basic SEM models, these are what we will cover these 3 days. And then when I come, I'm going to talk some more advanced SEM models. So the easiest way, the simplest model is the PAP model with observed variables. It is nothing more than regression. We just put many regression equations together. Then we talk about the measurement model. That is what we will cover tomorrow. Then we will talk about full structural equations modeling with latent variables. And then the model with mean structures. The model with mean structures are actually not very meaningful. Sorry, Maxwell. It is not very meaningful. But on the second day when I come in our in-person class, I hope you will be there. When we talk about measurement invariance, that becomes meaningful. We can compare the means across groups. And I wrote a software that can compare the means across groups. That's something I will share with you on the 17th of June. So this is a PAP model. We will start with the easiest thing. This is a PAP model. We consider this as all observed variables. Here is called a trickle-down effect. How the supervisors' interpersonal justice and informational justice will affect subordinates' interpersonal justice and informational justice. It is through the supervisors' perceived organization support, their supervisors, their managers' role model influence, and their anger with the organization. How this will affect, this becomes the mediators. So the supervisors interpersonal justice will affect subordinates interpersonal justice through their mediators. This is the model that we are going to test. Before we test, I need to introduce two terms to you. The first one is called exogenous variables. The other is endogenous variables. Exogenous variables are variables that act as a predictor or cause. So these are independent variables. In the diagram, these are the variables which only has arrows coming out from them. So here, there are two boxes. In SEM, a box means observed variables. A box means observed variables. A circle means, or ellipse means latent variable. Here, in PAP analysis, we deal with observed variables. Here, there are two variables which are exogenous because they only have arrows coming out. They don't have arrows going in. These are exogenous variables. Endogenous variables is an independent variable or outcome variable in at least one relationship. Here, obviously, subordinates interpersonal justice and the subordinates informational justice are endogenous variables because we have arrows going in. For supervisors POS, managers role model influence, and supervisors anger, we have both arrows going in and arrows coming out. These are all endogenous variables. As long as there's an arrow going in, it is called an endogenous variables. That means somehow it serves as a dependent variable. Xinhua asked earlier about the default enables. In fact, in all SCM softwares, there's a default. We covary the exogenous variables. There's a covariance between these two. Now, when we have a dependent variable, we don't talk about their covariance, but we talk about the covariance of their residuals. What that means is, I'm going to draw something here. What are these two arrows? This as a dependent variable. We have some variables to predict this variable, but then there it cannot predict 100% of the variance. There is a residual here. So whenever we talked about endogenous variables, we talked about the residuals and the covariance of the residuals. Covariance of the residuals, not the covariance of these two variables, but the covariance of these two residuals. And interestingly, in Amplus and Verne, most of the softwares, they also covary these two residuals. What that means is there may be some other variables. Another variable here. It may affect this and this. In this particular case, if you do not have this variable in your model, then the residuals will covary. The residuals will covary. Okay, but you know what? You cannot add all possible variables in the model. There's no way you can include all possible variables in your model. So instead, we will typically allow the residuals to covary. Okay. Now I got two questions. Sally asked, this square means the survey items. Okay. If you use surveys, for example, if you have 4 items, if we are talking about observed variables, okay, these are not proper SEM. This is a path diagram. If you have 4 items, we take average of the 4 items and treat it as the observed variable for supervisors interpersonal justice. If you have 3 items for supervisors POS, then we use the 3 items. We use the 3 items, take the average, and represent the supervisor's POS. Okay. So this is not full SEM. For full SEM, we will analyze at the item level. But for path analysis, we take simple average of the items to represent these latent variables as if they are directly observed. Maxwell asked a question about control variables. I think last week I talked about control variables. What are control variables? Control variables are simply independent variables that you're not interested in your study. You're not making contributions from the control variables. If you want to include control variables, now I have 2 control variables here. I just do them like this. This is how to add the control variables. Now you can see that they are the same as the supervisor's informational justice or supervisor's interpersonal justice thing. But we are not interested in this two theoretically. Therefore, we call them control variables. Okay? Now, finally, we are going to run Laverne. You installed Laverne on your computer? Laverne and SEM tools? First, you must have R on your computer. No matter whether you use R Console or R Studio. Thank you, Kate. So if you have R, I'm going to show you my R. Here. This is my R when I open it. I don't have the, I didn't install the latest version. So before, you need to install the R. Okay. If you have any questions installing the R, okay, I will give you an early lunch break, okay, but I will stay here to work with those who have issues, who have problems in installing the packages. So we need to have, basically, we need to have Laverne and SEM tools. Laverne is the SEM software in R, okay? SEM tools is a collection of many different tools that can facilitate you to do your job easier when you run SEM. Therefore, we typically will install this tool and run this tool. Be very careful when you use any functions in SEM tools. I found there are many tools which have errors, which are wrong, okay? So be very careful when you use SEM tools. When we use Laverne or SEM tools, every time you use your R console, you launch your R console or R Studio, you need to load Laverne and SEM tool once by typing library in parentheses Laverne and library SEM tools. I showed you, for example, here, if I type library, Laverne, you will see a welcome message. Type library, SEM tools. You will see another SEM message. Now, be very careful in R. The capital letter, the uppercase and the lowercase are two different letters. So you have to follow exactly the same Laverne and all lowercase SEM tools, and T is the uppercase. If I try to type like all capital, it will give you an error message. There's no package called Laverne. In fact, I have Laverne, but it is all lowercase. It is not uppercase. So be very careful when you type in R, lowercase versus uppercase. Before you run anything, you need to have library. You better to load the Laverne, library Laverne, and library SEM tools. And I usually what I will do is I will change the working directory to where I have my data file. I suppose you have downloaded all the files I sent you. Okay, so that we need for these few days. So what we can do is go to File, change directory. Can you see it? No, it's my screen. Where's my screen? I may be using. I found it on my different monitor. So when I change directory, it will show this thing. Okay, and I have my data in SCM workshops introductory SCM with R. So I select the folder. Okay, this is one way. The other way is RStudio. A lot of people like to use RStudio. I don't like to use RStudio, except when I write my programs. You can see that I'm writing programs here. So here, you can also do is library, Laverne, and library SEM tools. You only need to type it once. You only need to type the library once when you open the RStudio, okay, or our console. When you can run multiple programs, okay, you can run multiple programs. Here, how can we change the directory? Okay, let me clear the console. Go to section, set working directory, choose directory, and this is where SCM workshops, introductory, SCM with R. You can see, in fact, it automatically type a command. This is how you can open Laverne using RStudio. Well, different people have different opinions, okay, preference. I only use RStudio when I write my programs because it is the only way that I can do. The reason why I don't like RStudio is that you can notice that it chops off my screen. Well, I have a very big screen, okay, 27 inch. I have two 27 inches screen, but it chopped off my screen into smaller sections. Okay, that is one thing I don't like because I need more space to work on. This is the reason why I don't like RStudio. Anyway, okay, so we have library. We set the working directory already. Have you done that? Hello?
Yes.
Okay, I hope we can do it together. So before you run anything, you need to have installed Laverne and SCM tools, and then we have library, Laverne and library SCM tools. Change the directory to where you save your data file. In that way, you do not need to type the path for your data file. Otherwise, you will need to type the path for your data file. Next slide is okay. In running Laverne, okay, running SCM Laverne, there are 5 steps. The first step is to import the data. Then you specify your model, you estimate your model, you retrieve your results and save the results. I really don't understand why they don't combine the 5 steps in one. Okay, they make you do like Mplus, they combine all the 5 steps into one. But in Laverne, you need to do it in 5 different steps. Import data, model specification, model estimation, retrieve the results, and save the results. Step 1 is to import data. Typically in Laverne, I will run on a CSV data file. Okay. You read the data file, CSV data file, For example, you should be able to find an example underscore a1.csv and read CSV into the system. We call this a data frame. We convert a data file, CSV file, into a data frame, and in this data frame, we call this an example.a1. Oh, by the way, this year I make it a little bit different. In your files, you should be able to find a lot of files called outcode. Can you find outcode example a1.txt?
Yes.
This is the file that you have all the codes. You can copy and paste from here instead of copying from your PowerPoint. Okay, because for PowerPoints in the past we always have problem with the quotation. So the first thing is, see my slide. If I copy and paste this, copy my R, is here. Now I have read example underscore a1.csv into a data frame called example.a1. How can you know whether you have successfully read that? If you type example.a1, because it has many lines, if we just type this and hit enter, you can see there are 200 lines. It has 7 variables. These are the variable names. Because it's too long, typically I would do is example.a1. I just want to show the first 5 lines here from 1 to 5 and a comma and a square bracket. Then it will give you the only for the first 5 and variable name. Have you read your data file?
Yes.
Okay. Now, maybe I should also show you how the Excel file looks like. This is what the Excel file looks like. The first row includes the variable names. The variable names. Be very careful again, because R is sensitive to uppercase and lowercase. If you put uppercase here, you need to include all uppercase. If it is uppercase and lowercase, you need to have uppercase and lowercase. The first row is the variable name, and then you have your data. What if you have missing data? If you have missing data, just leave it blank. If you have missing data, just leave it blank. Okay? Now, slide PowerPoint here. Okay, so this is the first step. We import the data as a data frame. Second step is to define the model. These are the commonly used operator of Laverne. I'll go over this. If you want to estimate a covariance that we will use later today, here means that X covariant with Y. Okay, if you want to specify a covariance between X and Y, there are 2 slits. If you want to estimate a regression, for example, use X to predict Y, then we have Y as a dependent variable, select X as an independent variable. In the measurement model, if we want to define a reflective latent variable, f is a reflective latent variable, we use equal and SNCC x1 plus x2 plus x3. That means we are using x1, x2, x3, these three indicators to measure the factor f. By default, Laverne will fix the factor loading of the first item, first indicator to 1. If you want to override this default, we put down NA star. Okay, we seldom use this. Minjie asked for how to define a formative latent variable. In Laverne, it is a lot easier. You use this sign and the snake. Here, that means x1, x2, x3 are formative scale of the factor f. If you want to estimate the intercept as well, especially if you have the mean structure, which is SNCC1. I hate this symbol. I always make mistakes with this symbol. Okay, x1 SNCC1. If x1 is the item, that means the intercept of the item x1. F SNCC1 means that we are estimating the intercept or the mean, the latent mean of the factor f. We can label or fix a parameter using the asterisk. Here, f 1 star x1, that means the factor loading of x1 is 1. The factor loading of x2 is labeled as b2. The factor loading of x3 is labeled as b3. You can also constrain parameters to be equal, especially if you want to do equivalence test. But remember, in R, equal is not one equal sign, it's two equal sign. I make that mistakes all the time. Okay, so B2 equals to B3 needs two equal sign if you constrain them to be equal. If you want to create a new parameter, okay, is semicolon equal, then you can create, for example, if you want to estimate the mediating effect, we need to multiply the coefficients of two powers B2 times B3 that form a new variable, a new parameter, B2, B3. You are creating a new parameter, B2, B3, which is B2 times B3. Insert a comment in the syntax is a pound sign. Everything after the pound sign are comments. These are the commonly used operators that we will use with Laverne. Okay, and we will use those except for formative latent variable. We will use this in the coming week, this week and next week. Be very, very careful. When I work on all these PowerPoint slides and exercises, I always make this mistake, the regression. This is one stick, one snake, okay? I always put equal and snake, okay? That becomes a measurement model. A regression model is only one snake. We will go over this again and again. Basically, what you need to know to start with is the equal snake and the snake. But today, we are not going to deal with the measurement model. So we are dealing with the path model. So we will only use the regression, the snake. Before we write the syntax, I always label all the paths. This will be a lot easier later on when you read your results, when you will know what paths you are referring to. Here, you will notice that this diagram and the previous diagram, the difference is that in addition to all these labels, I also add a direct path from supervisors interpersonal justice to subordinates interpersonal justice. and supervises informational justice to subordinate informational justice. Of course, you can also add a direct path from supervises interpersonal justice to subordinates informational justice, and supervises informational justice to subordinates interpersonal justice. But they are not making too much sense. I didn't include them in the model. I only include this direct path and this direct path. Okay. I will explain later why we have to include the direct path. In fact, whenever you estimate a mediating model, you have to include the direct path. So step 2 is to specify the model. A path model is within quotations, within two quotations. The first line here, model.A1 is the name of the model. You give a name of the model, whatever you want. I call this model.A1. You give a name of the model. This smaller sign is short and hyphen. This in R means equal, or I assign this measurement model and call this model.A1. Okay, it's a quotation. Let me explain this. According to our here, according to this diagram, POS as a dependent variable has two errors going in, supervises interpersonal justice and supervises informational justice. So first, I write an equation. POS regression is one leg. The label is A11 times supervises interpersonal justice plus A21 times supervises informational justice. Can you follow? Do you know how I get this line?
Yes.
Then we will do for RMI, role model inference is A12 times supervises interpersonal justice plus A22 times supervises informational justice. So the second line is RMI regression. A12 times supervises interpersonal justice plus A22 times supervises informational justice. So I strongly suggest you to use one equation for each dependent variable. Then the next one is anger. Okay, so we have two coming in as well. Anger. And then for subordinates interpersonal justice, we have supervises POS, B11 times, B21 times RMI, B31 times anger. We also have a direct effect. You can have B11 times POS plus B21 times RMI plus B31 times anger. You can also add the direct effect here, but I add it on a separate line for the direct effect. So you can see that I have a pound sign and put down direct effect to clearly specify that this is the direct effect. So I do it for subordinate IFJ as well. The last line is what Xinhua has asked. In fact, you don't need to specify it. It is by default. It is covering the residuals of these two. It is actually, it will do by default. The second step is we specify a model like this. Now, if I copy and paste this to R, so I've read model.A1. If I type model.A1, oops, no, it will look pretty bad. Okay, if I type CAT model.A1, it should looks better. Yeah, this is my model.A1. Are you on the same page? Are you following? Okay. Next, we estimate a model. Now, when you estimate the model, interestingly, Laverne doesn't distinguish between SEM and CFA. In fact, it is not CFA, confirmatory factor analysis. So we type SEM is the function. SEM is a function. The minimum thing you need to do is you run SEM on your model and your data. Your model is model.A1, your data frame is example.A1. You run your model and you save all the results. We call it in a subject. Subject is, we give it another name, a subject name called EST model.A1, estimated model.A1. So we run our model and save the results in a subject EST model.A1. You will notice that I also add two things. This is the first step. There are some decisions you need to make. The basic decisions that I will make is your estimator, we use maximum likelihood. Information equals to observed. Information equals to observed. There are two possibilities for information matrix. Information matrix is a matrix that the SEM software used to compute the standard errors. Information equals to observed is to use the observed information matrix, which is the default in M+. And it is more appropriate if you have missing data. The default for Laverne is expected, which I don't like. So I always put down information equals to observed. Okay. There are few default values of Laverne that I don't like. I will tell you later. Okay. So here actually it is 19. I put down SEM, your model name, the data frame name, estimator, and information equals to observed. If we put this, copy and paste this to R, okay. This is our step 3. Do you notice that you don't see anything? This is a good sign if you don't see any error message. Step 3 is model estimation. Okay, we have finished step 3, model estimation. Now, step 4 is to retrieve the results. We have an object, estimated model.A1. The keyword, the function is called summary. As EST model.A1, we ask for the fit measure, we ask for the standardized coefficients, and also we ask for the R square. So there are different ways, different results that you can ask, but this is typically what we will ask. You put down the object name, we ask for the fit measure, the standardized coefficient, and the R square. Okay. Now you can see the results. We have all the fit measures here. We have the estimates with all the labels, estimates, the standard error of the estimates. Nowadays, it is a common practice for you to report the estimate and the standard error of the estimates. So you need to report estimate and the standard error of the estimates in parentheses. And usually I will also report the standardized all, okay? You have the Z value, which is the estimate divided by the standard error, the Z value, and the P value. People like to look at the P value, whether it is lower than 0.05 or 0.01. okay, to show the significance of your parameter, you will see there are two standardized values and they are different. Okay, we ask for the standardized results, they are different. The first standardized results only standardize the latent variable. But what we should do is to use the standardized all. That means standardizing both the observed variable and your latent variable. So whenever you report the standardized coefficient, you should report the last column. When we will use the standardized the latent variable only, if your observed variable is a dichotomous variable. If your observed variable is a dichotomous variable, then you cannot standardize your variable. For example, gender, you have male and female, you have 0 and 1. You cannot standardize 0 and 1. Then you will use the standardized latent variable only. Otherwise, you should use the standardized all. We also have the covariance. The standardized all refer to the correlation of first estimate is the covariance. The standardized all is the correlation. Lastly, you have the R square. You have the R square. Finally, how to save the results. If you use R console, you can go to File, Save to File. Then you can save your results to a file. Okay, and then you hit Save. If you use R console, it's more complicated. I don't know what is a good way to do R console, R studio. You need to copy and paste. If you want to save the results here, you need to do copy and paste of the pattern now. I don't know. No. Okay. So the 5 steps. Let me repeat the 5 steps. Import data, specify your model, estimate your model, ask for the results, and save the results. Now, the next step is we got the results. Are they good or bad? We don't know. So, how to read the results? The first thing we need to do is actually check for unreasonable parameters. What are unreasonable parameters? For example, negative variance or correlation greater than 1. Why we will have unreasonable parameters? If you go back to your results, do you see all these estimates?
Yes. Yes.
How SEM works is, in fact, it has a set. Different software has different way to generate one set of starting values. That means Laverne will plug in a values, all these estimates first. And then it will calculate a fitted covariance matrix. It will calculate a fitted covariance matrix. And then it compare with the sample covariance matrix. And then Laverne will change the estimates a little bit, change these numbers a little bit, such that the fitted covariance matrix will be different. And then it compare with the sample covariance matrix again. It will see whether these delta estimates become smaller or not. If it becomes smaller, it will further change these estimates and trying to find a small all delta estimates until it reach a minimum and go back, then it will stop. This is where Laverne find the set of parameters that will give us the smallest delta estimate. It is an iterative process. Therefore, in the first line, you will notice that it says Laverne ended normally after 16 iterations. So after 16 iterations, it finds the minimum delta estimate. It is an iterative process, and that shows you 16 iterations. However, interestingly, all the softwares will do that. If your model is not very good, it will even try to change the variance to a value, to a negative value. The variance, the minimum possible value for variance is 0. But because it tries so hard to find the minimum delta estimate, it may even change the variance to minus, or it will change the correlation. It will change the correlation to larger than 1. These are what we call infeasible solution. And if that happens, you will see a warning message here. Here we don't see a warning message, so we don't have any problem. You don't have negative variance or correlation greater than 1. If the model has to do that, then it will give you a warning message. Typically, if you do not run a mean structure, if you do not ask for the intercept, it won't happen. Okay. It will only happen if you have complicated models. So the first step is to check for unreasonable parameters. In the past, we have to check it manually, but nowadays, if there are any unreasonable parameters, you will see a warning message. Then we need to look at the model fit before we look at the parameter estimates. Remember, you must have a good model fit before you can interpret the parameters. If you do not have a good model fit, never interpret the parameters because the parameters are wrong, because your model is wrong. Your model doesn't fit the data. Then why should you interpret the parameters? Model fit refers to the delta estimate. Gabor has developed about 50 different fit indices to estimate, to measure this delta estimate. More than 50 different fit indices to measure this delta estimate, okay? But there's some more commonly used than others. I told you that the softwares are trying to minimize the delta estimates. In fact, it is trying to minimize this equation. It is comparing the fitted covariance matrix with the sample covariance matrix and using this equation. The first fit index that people use is chi-square, which is n-1 times the minimum fit function value. The minimum fit function value is an equation that compares the elements of the fitted covariance matrix and a sample covariance matrix. So first test people will use is the chi-square test, because a chi-square test has a p-value. It has a known distribution. Therefore, some researchers like to use the chi-square test. But here, one thing that you may notice is that FML, the minimum fit function value, has nothing to do with sample size. It only compares the elements of the two matrices. The chi-square value, on the other hand, heavily depends on the sample size. What's just the minimum sample size that you should run with SEM? It depends on the complexity of your model. Typically, if you have 200 or more, that is fine. You can publish in management journals. If you have an organization level study, 150 is okay. In marketing, when they run experiments, they typically has a smaller sample size. But the smaller sample size you have, the more unstable are the estimated parameters. Okay. So don't have too small sample size. I would recommend at least 200. We'll talk about MLR later. Maxwell, you have a question? You just type. I will talk about the okay. What is a large sample size? Interestingly, it very much depends on your discipline. SEM requires large samples. In fact, SEM is the results are pretty unstable. If you are a statistician, okay, a small sample size is 500. A medium sample size is 1,000 to 5,000. They can have 10,000. Okay, so this is what they usually have in their simulation. 500 is small sample size. But for us to do empirical studies in management, in marketing, in psychology, 500 is a very large sample size. You are lucky to get a 200 sample size. Okay, so if the sample size is over 1,000, okay, I don't understand what you mean by significant, Maxwell, when you say make the model significant. Okay, so
I mean,
we,
is that likely if I only have a 200 sample size and then the some path is not statistically significant, but when I increase the sample size from 200 to 1,000
okay,
more, and then everything become more statistically significant. That's my question. Thank you.
you're cheating. Okay, now let me show you my result. Okay, my result is here. So Maxwell asked, we have an estimate. If we increase the sample size, for example, here we have a path which is not significant. A2D is not significant. If we increase the sample size, what is the effect of increasing the sample size? The standard error for A2D will become smaller and the p-value will become smaller. Yes, the answer to your question is the larger the sample size, it is more powerful. That means even for the same estimate, it is easier to get significant results. However, the major problem is here. If you have a very large sample size, even a very trivial, very small minimum fit function value, that means very small discrepancy between the delta S and delta fitted covariance matrix, it will reject your model. That means the larger the sample size, this is easier because any slight differences, trivial differences of your model to the data will reject your model. Then you cannot interpret your parameters. Do you understand what I mean?
Yes, sir. But my experience is even with like a 200, 250, and sometimes we have a very significant chi-square that will lead us
Yeah.
to suggest the model does not perform.
Even if you do not look at the chi-square, even if you look at other fit indices, they are not as sensitive as chi-square to sample size, but still they are affected by sample size. They are still affected by sample size.
Yes, sir. Thank you. Thank you.
Okay, so if you get 1,000, I've only published 1 or 2 papers with more than 1,000 subjects. So unless your model is very good, otherwise having such a large sample size will not be at your advantage. Okay, so there is a chi-square test. Sometimes later on, I think tomorrow, I'm going to suggest you to run, instead of using maximum likelihood, I would suggest you to use maximum likelihood with robust standard errors, an MLR estimator. Because like regression, we typically assume that our data are normally distributed, but actually a lot of cases, our data are not normally distributed. So we should use the MLR estimator, which are better for non-normal distributed data. So here, we will make an adjustment to the chi-square. Okay, so you will see a different chi-square with a scaling correction factor. We will talk more about this tomorrow. What are the fit indices that we should report? You have to report chi-square, but nowadays nobody look at the p-value of the chi-square. If you look at the p-value of the chi-square, most of the models will get rejected. So people created an index called root mean square error of approximation, RMSEA. Here is the equation. df is the degrees of freedom, which I will explain later. df, okay? So this is the equation. Typically for RMSEA, although it has a p-value and the confidence interval, typically we use a rule of thumb. If RMSEA is lower than 0.05, you have very close fit. If RMSEA is lower than 0.08, you have adequate fit. That is fine. As long as your RMSEA is lower than 0.08, then you can interpret your model. What I would say is our model fits the data adequately. If my RMSEA is lower than 0.05, I would say my model fits the data well. If it's lower than 0.08, I would say my model fits the data adequately. Although there's a suggestion that RMSEA greater than 0.1 is perfect, but nobody use this rule. All people use 0.08. 0.08. If you have RMSEA equals to 0.09, sorry, you cannot interpret your model. Otherwise, you will have a difficult time to explain to your reviewers. Interestingly, RMSEA also has a test. It tests whether RMSEA is smaller than 0.05 or it has confidence interval, but no people use this. No people use this. Okay, so all you need to do is to report RMSEA and see whether it is lower than 0.08. The lower the RMSEA, the better is the model fit. Another fit index that we commonly use is called CFI. This is a comparative fit index. This is the equation. You can see it is based on the model chi-square, model degrees of freedom, with a baseline chi-square and baseline degrees of freedom. What is a baseline model? A baseline model means that you only have the indicators, you don't specify any relationship. We don't specify any relationship. We only put the indicators in the model. The larger the CFI, the better is the model fit. The larger the CFI, the better is the model fit. This is from 0 to 1. In fact, if you use this equation, it can go over 1, but whenever it goes over 1, we truncate it, we put down it as 1, we treat it as 1. The rule of thumb is developed by Hu and Banner. They suggested that CFI should be greater than 0.95. But we usually use a more relaxed rule of thumb, is 0.90. We use a 0.90 instead of 0.95. Which rule of thumb you will use depends on what value you get. If your value is higher than 0.95, then you will say we use the rule of thumb 0.95. If your CFI is 0.93, then you don't want to throw your model away, then you will say our CFI is greater than 0.90. It very much depends on the complexity of the model, in fact. One last fit index that you should report is the standardized root mean square residual, SRMR. Here you can see that actually we are finding the average difference, square difference of each element between the sample covariance matrix and the fitted covariance matrix. We take the average and then the square root again. The smaller the value, the smaller the discrepancy. So the smaller the value, the better the fit. Rule of thumb is the value should be less than 0.08. SRMR should be less than 0.08. So let me repeat again, what you need to report. I typically will report chi-square value with the degrees of freedom. What means square error of approximation, RMSEA, CFI, and SRMR. Now, although we don't use chi-square, we typically will report chi-square. CFI, RMSEA, and SRMR, these three indices are sensitive to different parts of misfit. What that means is you have to report all three and make sure that all three pass the threshold. You cannot have just one or two pass the threshold. If one fails, that means there's something wrong with your model. So I have just answered the question on the chat, okay? You should report all three indices because they are sensitive to different parts of the model. There are some other fit indices. I told you there were 50 fit indices developed. In the past, people use GFI or adjusted goodness of fit, AGFI. I have a citation here showing you that these are outdated and these are no good. You should not report GFI and AGFI now. This is a fit index, which is very commonly reported in marketing, which I hate, okay? It's called chi-square divided by degrees of freedom. It's called lambda chi-square. The reason why I don't like it is because it is also sensitive to sample size. If you have a large sample size, you will fail again. So you cannot use it to replace chi-square. It has the same problem as chi-square. Another company use fit index is similar to CFI. It's called Tucker-Lewis index. Sometimes it's referred to as the non-fit index. It is similar to CFI. It compares the fit of a baseline model and your estimated model. It also has a value from 0 to 1. It also requires you to have TLI higher than 0.95. Actually, if your model is good, CFI and TLI are highly correlated. They are very close together. So I don't report TLI. If your model is bad, then it may not show up in CFI, but it will show up in TLI. Can you follow? If your model fit is bad, you may still get a good CFI value, but your TLI value will be very low. Okay, I'll show you an example very soon. There are other fit indices for you to compare the fit against different models. For example, the AIC, BCC, but I don't encourage you to use any of this because we usually do not compare fit indices across non-nested models, CAIC and ECBI. Now, if we go back to your R output, I have chi-square equals to, do you notice that there are two sets of chi-square? Model test user model and model test baseline model. You should read the model test user model. The test statistics, this is the chi-square 25. Degrees of freedom is 5. P-value is significant. That means if you look at chi-square, it will reject your model. Okay, but well, we report it. We don't need to look at it. CFI 0.924 is about 0.9, which is good, right? Okay, but do you notice that the TLI is way below 0.9? That means it is an indication that something wrong with your model. Something wrong with your model. If your model is good, it should be very close to the CFI. If your model is bad, it will be very different from your CFI. If you look at RMSEA, it's 0.142. Okay, sorry, it is higher than 0.08. So RMSEA failed. SRMR 0.048. Now, do you notice that CFI is about 0.9, which is fine. RMSEA is above 0.08, which is bad. SRMR is below 0.08, which is good. That means we need to reject our model. Our model doesn't fit the data well. Although the CFI is above the threshold, the SRMR is below 0.08, we still cannot interpret the parameters because our model doesn't fit the data well. Have I made myself clear? You need to look at all three fit indices. All three have to pass the threshold. So, a model doesn't fit the data. What can we do? Okay. In that case, then we can ask the learn to give you the modification indices. What are the modification indices? Modification indices are, in fact, there are some paths that we have not included. Modification index is if we estimate this path, how much the chi-square can it be improved? That is the modification indices. Okay, so it calculates for each constraint relationship possible in the specified model. It is the value if you estimate that how much the chi-square can be improved. So what we need to do is to now to put down summary, your object. We don't need to run the burn again because we run it already. So it is all the information are saved in the object. We put down modification indices to true. So our estimated model, our object is EST model.A1. Modification indices equals to true. Now put this command into so you can see the modification indices. Okay, all the estimates again, the modification indices. MI. Okay. then it will tell you the expected change as well. So here, the first one, for example, if we relax the variance of the supervisor IPJ and supervisor IPJ here, well, it won't change anything. Okay. So here, what we will look for is the parameter which has the largest modification index. Do you see that row number 4 has a modification index of 20.968, 13, 20.968, 17, 20.968. What is row number 4? Row number 4, because POS and RMI are endogenous variables, these two slicks means that the covariance of the residual. Now we have not estimated covariance of the residual. If we estimate the covariance of the residual, the chi-square can be improved by 21. Similarly, if we use RMI to predict POS, we can improve by 21. If you use POS to predict RMI, we can also increase the chi-square by 21. Now, this is exactly the reason why we should do hypothesis testing. Now you can see that either path, any of these three paths, if we estimate, we will get a good fit. Then which path should we relax? It very much depends on the theory. Okay, but here I have a theory. Here you can see these three paths. The theory is that I'm going to go back to the figure here. Do you remember that we covary the residuals of the dependent variable by default? That means we may have some other variables that will affect these two. But I don't understand why the softwares do not covary the residuals of these three parallel mediators by default. They are not pointing to each other, so I call them parallel mediators. They have residuals. So we should, there may be some other variables that affect these variables together. So what the modification indices, the first modification index suggests is that POS covary with RMI, the residuals. That means there is a different variable that affects both POS and RMI that we have not included in our model. Let's see how we can include this. Here, the line in green is based on the previous model. Now I add POS SNCC RMI. Instead of just adding one correlated residuals, I add all three correlated residuals. Okay? So this is our revised model. Let's run this model. Next thing, there's no error message, no warning message. Means the variance and the correlations are fine. Then if we look at the fit indices, chi-square now we got 2 degrees of freedom, chi-square is 1.106, and even the chi-square, the p-value is not significant. CFI is 1. RMSEA is 0. SRLR is 0.011. That means our model fits the data very well. Okay. So if we add back the Maxwell asked about the value of TLI, which is greater than 1. As I said, we showed you the equations. This equation allows TLI to be slightly higher than 1. For CFI, it will never be higher than 1 is because whenever it is higher than 1, it will report as 1. Okay, so theoretically, it can be go over 1. Of course, it means it is a very good fit. It is good fit. Now, these are the fit indices. So the first step is look for warning messages, whether they are negative variance or correlation higher than 1. Then we look at the fit indices. The fit indices show that our model fits the data well. Finally, we can look at the parameters, estimated parameters, to see whether they are significant or not. Do you hear my cat yelling, ask me to open the door for him again? No, sorry. So he will come in and out for 10 times a day. Here, covariance. So when you see that, okay, the POS and RMI, now it has a significant covariance. The other two are not significant. Okay, that is fine. Now, the problem is whenever you use the modification index to change your model, it is sample specific because the modification indices are estimated based on your sample. You cannot use modification indices to change your model and report the results unless you found that you have made a mistake. Here, I would say you have made a mistake. So when slide 56 gives you the citation for correlating the parallel mediators. Parallel mediators. This is a citation. Slide 56. So what that means is, in fact, provided with that citation, we should actually at the very beginning not estimating our previous model. We should estimate this model. We simply made a mistake. Then I won't tell people that I use modification indices. I will just report the model with all these covariance of the residuals. If you use modification indices to add a path without any justification, then that will be sample specific. You have to collect another set of data to test your model because your model will always be correct if you use modification indices to change your model. Do you get my point? You get bad model fit. You can use modification indices to find out why. If it is you made a mistake, for example, you miss out a direct path, then you can add it back and see if it is your original model. But if it is not a direct path, if it is a path that you have not hypothesized, then you have to collect another set of data to test your model. Here, we have run two models. Model A1A, which doesn't have the covariance, and model A1B with all these covariance among the parallel mediators. Now we can introduce the concept called nested models. Okay, I'll keep this in the afternoon. That's what I'm covered in the morning. Okay. If you have installed your Laverne, then you can have an early lunch. What time do you have now? What is your time now? 11:45, right? We will be back at 1 p.m. Okay, you can have lunch. If you do not have Laverne, if you have problem in installing the Laverne, please stay and we can work together. Okay? Yeah. For those who finish, you can go. For those who have Laverne, you can go. Does anybody need help? Does anybody need help in installing Laverne? Hello? No? No of you have installed? Oh, so I gave you 15 minutes extra for your lunch. Okay, I'll be back 5-10 minutes early. Okay, so I'll start at 1 again. Enjoy your lunch. Somebody has a question? No?